So now that we're happy understanding what an acid is, let's look at how we measure that acidity. It was Søren Sørensen, the Danish chemist who worked at the Carlsberg laboratory trying to understand everything there was to know about beer. He realized that the acidic strength was related to the concentration of the hydrogen ion. Now, the strength of the hydrogen ion, or the concentration of it, was very, very low, and the difference between a strong acid and a weak acid was so great that he realized that a logarithmic scale must be used to describe how acidic a substance is. And his scale, the powers of hydrogen scale, is what we now know as the pH scale. There's always been natural indicators, everything from red cabbage to basically purple flowers, which turned into litmus paper. We've known for a long time that acids will change the colour of certain chemicals. And so what they did at about this time was they managed to make a chemical, a mixture of other indicators that could indicate colour change at every different point on the pH scale. Now, the colour that something would go under these indicators was how the strength of the acidity used to be known. You see, universal indicator combinations of things like methyl red and phenolphthalein and thymol blue would create a full range. Now, we're quite used to still working with phenolphthalein because it has that wonderful colour change when it goes basic or alkali. It basically turns luminous. Let's take this opportunity to take a close look at phenolphthalein. So phenolphthalein is, well, cloudy, white or colourless in acidic and neutral solutions, and then goes hot pink in alkali solutions. So let's have a little look at why that might be. First of all, phenolphthalein is a synthetic molecule that is derived from phenol and phthalic anhydride, and it looks like this. It's got these, well, it's got all sorts of things, including oxygen, hydroxide groups, and these benzene rings, which we're not thinking about right now. Basically, in an acid, it is protonated. There are hydrogen bonds between hydrogen ions and the rest of the molecule, and these prevent the molecule from absorbing light in the visible spectrum, rendering it colorless. But when the acidity becomes very alkali, then it starts to deprotonate the phenolic groups. And the phenolphthalein, there's a lot of pHs in this. The phenolphthalein then significantly changes. A charged oxygen atom in the atom enables it to start absorbing yellow light, meaning that it transmits magenta or hot pink to me and you. But what is most important here is it would be very nice to be able to represent what was going on in terms of something other than the colour change of an indicator chemical. And so Søren Sørensen came up with this logarithmic scale, which referred to the concentration of hydrogen ions. What he thought was that maybe there was a 0 on this scale, which represented to it all being hydrogen ions. Now, in reality, we don't see this. This is not a thing. But what we can get is chemicals where the concentration of hydrogen ions sits at about 0.1 moles per decimeter cubed. And if you look at that, what would make 0.1 would be 10 to the minus 1. And then what would be 0.01, a dilution 10 times that, would be 10 to the minus 2. In fact, basically what we can see is we can represent these very, very small numbers, these dilutions, these fractions of 1, by raising 10 to the power of a negative number. And as that negative number gets higher, the actual number that is equal to becomes much smaller. And one way of instantly decoding this is 10 to the minus 4 has 4 zeros before the 1. 10 to the minus 9 has 9 zeros before the 1. What you can see is that the concentration of the hydrogen ions, the difference between something that is pH 1 and something that is pH 14, is actually in the hundreds of billions. It is a massive difference in the concentration of the hydrogen ion. So using a logarithmic scale enables us to express these great differences in concentration by saying it's pH 2 or pH 4 and that's very convenient for us. So in a formula, we could work out what the pH was. All we'd need to do on our calculator is put negative log, which would be to the base 10 in this instance, but it's the button on the calculator that just says log, of the concentration you're talking about, the concentration of the H plus ions. Now we could rearrange that. If we had the concentration, we could find the pH. It would be 10 to the minus pH would equal that concentration. And important, one change of pH represents a 10 times difference in the dilution or in the concentration of the hydrogen ions. So here I've given a concentration of H plus ions as 4.9 times 10 to the minus 3 moles. Inserting this into the formula above, can you work out what pH this would be? Substituting straight into that formula, it comes out that the pH would be 2.31. Let us have a look at the pH of strong acids. And by strong acids, I mean monobasic acids that completely dissociate all of their hydrogens into solution. These are straightforward. And what we're going to use is a new notation here. We start to represent the acid, or basically the conjugate base pair of any acid, as the letter capital A. So that in the form of hydrochloric acid, A would represent the chlorine that is bonded to the hydrogen in the hydrochloric acid. And what we see is that this goes and dissociates, and it separates whatever A is from the hydrogen ions. Most important is that this is true for all monobasic acids. It's a general formula. Also true is you can see that 1 mole of HA would produce 1 mole of H+. It means that from the concentration of H+, we could directly infer what the concentration of HA would be. In other words, yes, the pH is related to the concentration of the H+ ion, but this is going to be the same concentration as the original acid. So we can, from the concentration of the acid, directly work out what pH that acid would be. So here in this photograph, I've got all of our acids out, and you can see there's all the way from 0.01 mole all the way up to the dangerous 5 mole, which I'm terrified of. Can you work out what the pH of all of these acids are visible in this photograph? So you might have done this interesting and almost fun experiment of diluting acid. You take 1 molar hydrochloric acid and you dilute it at a ratio of 9 water to 1 acid, and it creates a diluted version of the same acid, 0.1 times as concentrated. And then you do that again and then again, and each of these beakers turns out to be 1 pH different from the other. Now you might be asked a question where you're given numbers and you've got to work it out. What would be the change in the pH? So the question would be something like this: 25 centimeters cubed of 0.1 molar hydrochloric acid is diluted to 100 centimeters cubed. What is the pH before and after the dilution, and what is the change in the pH? So to calculate the pH before, the volume doesn't come into it. We just need to look at the concentration. Since this is hydrochloric acid, it's a monobasic acid. 1 mole of hydrochloric acid would be the same as 1 mole of the hydrogen plus ion, and so therefore what we can do is directly substitute into the pH equation the concentration of the hydrochloric acid. So stick 0.1 straight in there and we end up with a pH of 1, no surprises there. Now the second part of this has got to figure out what the concentration would be after we've diluted it. It's gone from 25 to 100. It means that, well, if we do 25 divided by 100, it means it's a quarter as concentrated as it was before. So if the concentration was 0.1 before, and we're now a quarter of that, 0.1 times a quarter gives 0.025. So that is the new concentration for this acid. So we put that into the pH formula, and it comes out with a pH of 1.6. which means the pH of 1.6 minus 1 The pH change was 0.6.